Okay, today we're really going to drill in and focus on what it means when I say that we have a conservative force acting and what that means in terms of energy. So let's get started. So when we start talking about conservative forces, what we're really talking about are forces that are going to operate within a system that are going to allow for complete recovery of energy. So that energy will slide from kinetic to potential or from potential to kinetic. A few examples we're familiar with is that elastic force, like when we were working with the springs or hair ties or rubber bands, as well as a gravitational force. So there are a few things that have to be in play before we can really look at whether or not we're dealing with a conservative force. So to start with, the system has to have at least two objects. And there has to be a force that is acting between a particle-like object and the rest of the system. So if we're dealing with like the tomato being thrown in the air, so there's a force acting between the tomato and the earth, because the earth was part of that system. When we change the configuration of the system, the force that's doing work on the particle-like object, the tomato in that case, that is what's changing the energy. It's transferring energy from one type to another. So it could go between kinetic and potential or some other form of energy in the system. So here is the big kicker, the big be-all, end-all of highlight. You have a conservative force if I reverse the configuration. The force will reverse the energy transfer. So if all of your energy went from kinetic to potential and we reverse the system, it now all goes from potential back to kinetic. Again, we are not creating energy. We are not destroying energy. It is just changing forms. Now you may be saying, okay, where is this at in my packet? This is not currently in your packet. This is extra. It's a little bonus, if you will. So what about a non-conservative force? What do we mean by a non-conservative force? A non-conservative force, by definition, is a force that is not conservative. So some examples. That would be friction. Another example could be like the drag force, like air resistance. Those would be non-conservative forces. They are taking energy out of the system. But if you think about the case where we're dragging something across the floor, if I drag it back and reverse it, I'm not putting that energy back. I'm taking more out, actually. So that's an example of a non-conservative force. You cannot reverse the process. So when we are looking at a non-conservative force, one of the bigger pictures that you'll see in a lot of physics books, and you'll hear about it, is the fact of path independence. So if I am going from point A to some point B, okay? So if I go from point A to point B, it doesn't matter if I go straight up and then over, or if I do some wonky turn. However I get from point A to point B, and from point B back to point A, whatever makes a closed loop, so closed loop from A to B, back to A, whatever path we choose, if we are dealing with a conservative force, moving an object between these two positions in a closed loop, that tells us that the work done during this closed loop by a conservative force. So we are path independent, so it does not matter what path we're taking. If we are going in a closed loop by a conservative force, then what can be said is that the net work done by the conservative force on a particle moving around any closed path is zero. So this is the net work done as we go around that closed path. So this is kind of one thing I thought was fairly important that we add in here. So let's keep going from some of our examples. So here we go. So we have a figure that's showing a thin rod, length L, which is 2 meters. So think about it like, almost like a meter stick, only it's 2 meters long. Has negligible mass. It can pivot about one end to rotate in a vertical circle. We have a ball that's attached to the other end. We pull it aside, 30-degree angle, and we release it with an initial velocity of 0. So as that ball descends to the lowest point, we want to know how much work does the gravitational force do to it? And what is the change in the gravitational potential energy of the ball Earth system? So let's start there. So the first thing that we need to do is we need to figure out what height did we release this ball? Because we need to know what is our displacement. So what we're going to do is we're going to go, okay, so let's use some basic trig. So this is our height, h. Okay, so if I look at this angle, this is 30 degrees. Okay, at the lowest height, this entire thing is L, right? So I need to figure out basically how big this is, because this is going to be L minus h, our height. So if we use our trig angles, we get that cosine of 30 degrees is going to equal L minus h over L. Well, L is 2, but let's keep this in alphabet soup for a minute. Cosine of 30 is going to be square roots of 3 over 2. I'm going to multiply that by L. That's going to equal L minus h. So that tells me that if I rearrange this a little bit, I'm going to move the h over and move this piece all the way back. So h is going to equal L minus L times square roots of 3 over 2. So that's going to be L minus, if I factor that out, that's going to be L times 1 minus radical 3 over 2. Now, why am I kind of keeping this like this? Because eventually this will be a different style of problem. And so you're kind of seeing that algebraic manipulation. So I have 2 times 1 minus the square root of 3 over 2. And that is going to give me my height. So this height is going to be about 0.268 meters. I'm keeping an extra decimal point in case I need that. So here we go. How much work is done by this gravitational force? So, well, what do we know about work? Work is going to equal the force dotted with the displacement. These are vectors, right? So I could do this a couple of different ways. I could do FD cosine theta. So let's just look at it the simplest way, which is to realize that if I look at the component, the distance we've dropped down, which is what I've done with all of this, then what I'm going to have is my force, which is mass times gravity, times my height. So this is going to be 5 times 9.8 times this height. So that's going to be about 13.1 joules. So that gives us part A. Part B says, what is the change in the gravitational potential energy? So we know change in the gravitational potential energy. Well, that's going to equal negative work. So that's going to be negative 13.1 joules. Okay, so C, if our gravitational potential energy is taken to be 0 at the lowest point, so if we declare this point to be potential being 0, what is the potential here? Okay, so I'm going to call it UI. Okay, so the potential at the initial point, if the bottom is 0, and we've dropped that potential energy 13.1 joules, guess what we had to start with? 13.1 joules. How do I know that? Because change is going to be the final minus initial. We know that the change was negative 13.1 joules. That's going to be 0 minus U initial, if we want to get fancy with it. Okay, so D. What happens if we change the angle? So, if we increase this angle, if we make this angle bigger, our height becomes bigger. So if theta is increasing, our height increases. So I would expect the magnitudes to be bigger because we are going to start with a higher potential energy every single time. So we would expect the magnitudes to increase. Now, obviously on part B, we're going to have a negative answer. That's why I'm saying the magnitudes, because it's going to be a bigger negative number.